memory safety for large C and C++ code bases that I gave a couple days ago at InfoSec World near Orlando in 2024. It is a talk about how to achieve memory safety, what memory safety is, both the technical aspects, as well as how to drive change across a large enterprise, because investing into memory safety and really achieving this can be kind of expensive. So let's get started. First, about me. My name is Florian Nöding. I'm a principal and security architect. I work at Adobe. I take care of product and software security, simplified, anything that isn't infrastructure. And one of the areas I invest heavily in is memory safety. And that is what I'm going to talk about today. So first, what is a memory safety vulnerability? And I picked a fairly old example. It's Heartbleed, because it affected probably hundreds of millions of users across the world. And it was very impactful. It allowed an adversary to extract arbitrary data out of the system running OpenSSL that was connected to the internet without leaving any trace. This is a snippet, slightly modified, from the source code of OpenSSL, an old version. And basically what happens here is, when you're asking the server, are you still there? You send this into the server a heartbeat message. And that's where the name comes from, Heartbleed, saying, hey, here's the type of the message, 1 byte, 2 bytes payload length, and then the payload. And then I can just say hello, and the server will respond with hello. And hello has HELLO, 5 letters. But the problem is here I can lie about the payload length as a client. And in the code, the following happens first. A buffer is allocated, and this has the right length. And then we are copying into this buffer, which is the destination, the heartbeat payload, the in-memory representation of what the client sent us. And then we use the payload length without validation, and that's the bug. Let's look at it, how it looks like in a memory layout. Well, this is simplified the memory layout. Some random data at the beginning, then we have the heartbeat packet with the source size, which we know how much data came over the network, and then some other data might be other network traffic. We can't really predict that, what's there. But if we lie about the payload length, this mem copy will copy a lot more. And that means this formerly blue part of the data which is now pink, gets leaked. And that means, because you can request up to 64 kilobytes of data, well, that's basically the amount of data you can simply steal and copy from a server's memory. And that's Heartbleed. Before we get into all the details, we need to discuss, why should we discuss memory safety? Why is this important? And it is simply important because it's the largest class of CVEs affecting C and C++ software. Now you might say, well, cross-site scripting and a bunch of other stuff is also really, really common. Yes, I agree. But in C and C++ software, that is the #1 weakness that we find. Microsoft has shared a study saying that roughly 70% of their CVEs are due to memory safety issues in their products. Google for Chromium has published a very similar statistic, also quoting roughly 70% of the critical and high CVs are due to memory safety issues. For Firefox, the basis of this number is a little bit different. It's 94% of all critical vulnerabilities are due to memory safety issues. So it's really important. And it shows that even experts, people that are really, really good at writing C and C++ code, struggle to consistently write safe code. I personally believe it's simply impossible. It's the same argument, why after more than 20 years do we still have cross-site scripting issues? Because we humans can't get things reliably 100% correct. And in C and C++, there are simply too many hazards that you have to deal with. And not only something relatively straightforward like an out-of-bounds access based on copying too much data, but also in a temporal fashion. You have to also reason about the lifetime of objects. And memory leaks are a problem in C and C++, so the safety concerns there are simply too. And probably most importantly, C and C++ are ubiquitous. They have found the foundation of basically the entire world's economy, operating systems, firmware, device drivers are all written in C and C++, and also many desktop products. So my company at Adobe's desktop products are largely written in C++ too, and we rely on lots of C code. Even if you use a more modern programming language like Python or Java, there's still a foundation of C and C++ there. So it's very, very ubiquitous. And the last part, why I believe this is also interesting to talk about, is there's a looming regulatory pressure. What do I mean by that? Governments worldwide, especially in Europe, with the Cyber Resilience Act, and here in the United States, with the Executive Order 14028, improving the nation's cyber security, we are seeing discussions about liability for software vendors for vulnerabilities in their products. And if you maybe in the future don't follow best practices about memory safety, you just might be found liable. Let's look at an excerpt from the United States National Cybersecurity Strategy, which was published in 2023. This is on page 19. And it says the administration will shape the long-term security and resilience of the digital ecosystem. They reshape laws that govern liability for data losses and harm caused by cybersecurity errors. And how will they do that? They'll use their purchasing power and grant making to incentivize the security. So at some point in the future, I believe it will be much harder to sell software that doesn't follow certain best practices. Before we can talk about where to invest, the key challenge is we have some limited resources. So we need to have a model of our adversaries that are trying to attack our software. And this is a highly, highly simplified model for this talk. So we have security research. They are generally friendly. They do responsible disclosure, have various motivations, and maybe they just want to have CVEs for their resume. Maybe they want to build up a reputation, maybe earn money via bug bounty programs. But generally, I don't think of the security researchers or bug counters as people that would submit 0 days and then exploit them. So it's an opportunity to learn. But generally, they will probably target software that is widely deployed, because widely deployed software is more well-known. It sounds better if you find something in widely deployed software. And we have e-criminals. And these are generally financially motivated. The idea here is e-criminals also run a business. Well, a criminal business, but still a business. And a business needs to be sustainable in some way. So the strategy of e-criminals is highly simplified. They need to find things that are repeatable and exploitable at scale. And that again points to widely deployed software. Finally, we have nation states. We know that 0 days have been and are being abused by nation state actors in targeted operations. From my perspective, that is rather hard to predict. So we need defense in depth in this case to protect against nation state actors. So now if you have a large code base, or maybe even many, many different products, what do you need to protect? How can we, instead of rewriting all C or C++ code in a memory-safe programming language, how can we be more precise? Because, well, if that would be the answer, the talk would be kind of short. So we need a smarter approach. So we start with widely deployed software. Anything that is installed across millions, tens, or maybe even hundreds of millions of systems, that's a good target. Or even widely deployed within a specific industry. If you talk about not IT infrastructure, but OT, for example, for the critical infrastructure, electricity, water, gas, things like that. And of course, handles untrusted input, because that is how adversaries get to this piece of software to try to exploit it. And then code involved in n-click attacks. What is an n-click attack? If you use a messenger application on your smartphone, somebody can just send you a picture. This picture will get rendered without any interaction at all from you. And if an adversary finds a flaw in this messaging app or one of the libraries it uses, well, they have a zero-click attack against you to achieve remote code execution within this program space. One-click attack would be double-clicking on a file downloaded from the internet, or opening an attachment from a phishing or spear phishing mail that you have received without any further interactions in the system. For example, if you've received a PDF, you open it in an app, and then the exploit is triggered. If there are still instructions in PDF, well, you have first to click here, well, then it's one click more. That's the basic idea. So we need to understand what code is involved in these end-click attacks. So I mostly work on desktop applications, and that is why I brought this example here. So how can we prioritize the risky areas and identify them in such an abstract desktop app? On top of the application, well, user-facing, we have the user interface. And I believe that's not really an interesting attack surface, because a user of the computer probably has access to much more. They can do more than just run your applications. They can only anyway run other applications. So that's not too much of a concern, even if it's written in C or C++. But what's really interesting is if you want to attack an application by end-click attacks, the file format parsing and decoding, and the libraries involved in that. So any code that handles documents, images, video, audio, and network data, if you have more network app, of course, and that is the area that you want to focus on first. If we imagine we have an image viewer, and after this file parsing, we need to render it. And we have an in-memory representation, because we are not going to have a different in-memory representation for bitmap files, PNGs, JPEG, and all the other formats. So the core of the application we need to secure somehow too. And later on, we'll discuss that that part is probably a little bit harder to say secure. If you have dynamic content, well, then the problem, of course, gets more complicated. This is not a talk how to secure a browser or a very complex PDF viewer that supports interactive content, but a little bit simpler applications, and an image viewer, an image editor, stuff like that. Let's talk about the first strategy, fuzzing. So what is fuzzing? It's coverage-guided testing with semi-random data, but what does it truly mean? So the first step is, well, we can first assume we have the source code of an application available that we want to test. And that means we compile this application, or ideally a library, with instrumentation. The instrumentation is supposed to do two things. While the application runs, we want to understand coverage. So which lines of code have simplified lines of code have been executed during this run. And if a memory safety issue is triggered, for example, an out-of-bounds access, a use of the free or something similar, well, the program should crash so that we can detect it. And then we generate semi-random inputs and just generate one input, run the program, see if something happens, and then we generate the next input. So we do that stuff. Then we run the target with instrumentation. So once for each input, and we observe if something interesting happens. So if there's a crash or we have new code coverage, then we save this input. And we do that again and again and again and again for maybe multiple days. Depends on how much money you want to invest to find memory safety flaws. So how does this look in practice? So let's go to Heartbleed back. So we have this mem copy, and we want to find a packet that we can send which lies about the payload length, so that we can trigger an out-of-bounds access that usually would have leaked the data, but because we now have a sanitizer running there, the instrumentation, it will crash the program. Let's send an empty packet. Well, that gives us some code coverage, so it's certainly an interesting input, and we'll mutate it, for example, by adding a single byte, and in this case, it's going to be the type of the message. We'll try 0, 1, 2. Eventually, we'll end up with hex 18, and that's a heartbeat message. Yeah, that's interesting too. Now we'll append some data. The payload length, this is kind of boring. 0 lengths, that will just work. After some time, we'll hit something like this here. Hex FF are 256 bytes, and then we have an out-of-bounds read, and that will crash the program. That's how fuzzing works in practice. What do we have to write? So basically, an engineer has to write something that looks a little bit like a unit test for a library. In this case, I'm using LLVM as a fuzzer. And by the way, in the appendix are lots of references. Go review them if this interests you. And this function is called with some random data and the size of the data. And in the rectangular area, the only thing that we have to do is, well, after first, of course, initializing OpenSSL library, we write this data into the OpenSSL handler, and then we say, please do a network handshake, which will ensure that the network code runs and processes the packet. And after running it for seconds to minutes, depending on how fast your computer is, you'll get a nice address sanitizer crash. And now you can go and debug the issue, and you found Heartbleed. That's how it works. And the coolest thing about fuzzing is that is a technique adversaries use too to find memory safety flaws. So by doing it yourself, you can emulate your adversaries and find flaws before they do. That's really awesome. But there's a problem. Unless your product is, or the thing you're working on is open source, this process doesn't work as is because you have to compile the target with instrumentation. So we can't really start there. So let's assume we have a host application, like an image viewer, which uses a library like libpng, libpdf, or maybe even a proprietary library where there's no documentation available. That's probably a better example. Then an adversary can use a debugger and attach it to the host application and observe the interaction between this application and the library. And they can create a harness, basically a small program that interacts with the library, uses dlopen on Linux or Mac, load library on Windows to open the library, call the init functions, and then the functions you want to fuzz. Then we can compile that harness. Then we generate input as is. But we can't easily run the target with instrumentation because we haven't compiled it in. So we need to do dynamic instrumentation. And there are several fuzzes out there, for example, AFL++ that can do that. And how that works is beyond the scope of this talk, but it works. It's just a whole lot slower. And then we do the same process. If we hit new coverage or crash, well, it's interesting input, and we go into this loop. Okay. So let's talk about why fuzzing. What are the benefits and the challenges with fuzzing? The biggest benefit is you don't need to make any changes to the product you're shipping. And if you are fuzzing libraries, it basically feels to engineers like writing unit tests. So this is very developer friendly, easy to get started with because they know how to use their libraries, so they can get started. At the beginning, you probably worry less about achieving high coverage, but just getting started with this journey is kind of important. And by fuzzing, if you have too much code to secure, you can also estimate the density of memory safety issues in a library or in a piece of code. And of course, as I mentioned, adversaries use the very same technique to find memory safety issues. The disadvantages are fuzzing of the host application instead of a library is much harder. And that goes beyond the scope of this talk. But you have to, the problem simplified is you have to start the whole program, run it, one input on it, and stop the program again and do it again and again. And it's very, very slow. So you need to make this process fast. There are tricks how to do that, but it requires a lot more work. And the another challenge with fuzzing as well is completely reactive. While you can do a lot of fuzzing, but even with a lot of fuzzing, you can't guarantee the absence of memory safety flaws. So you can be a little bit working ahead if you know adversaries targeted library, but depending on the corpus of inputs you use to seed your semi-random input generation, you'll probably not find everything. And unfortunately, it feels a little bit like whack-a-mole to your engineers who have to fix all these issues. So, second strategy, sandboxing. The idea here is to do fault isolation as defense in depth. So when we take, again, this file format parsing and decoding, the basic idea is let's move it out of the host application into a sandboxed area. And sandbox in the sense that we have memory isolation, because if the memory space of the host app and this part are distinct, memory safety issue is much less harmful because, well, you can't access the data of the host application. And if you combine that with limited privileges, well, getting out of that sandbox is probably kind of hard. What you have to do is, of course, then implement a file operation facade that proxies all the communication via remote procedure calls, inter-process communication. Well, it might be shared memory as a socket or other things. Marshals the data from the host app to the sandbox app and back again. And it's very important that the sandbox doesn't have access to the file system. So you can't send, or you cannot easily sandbox functionality that interacts directly with the file system or the other operating system. And if we have achieved good isolation, even if somebody achieves remote code execution within the file format parsing, decoding libraries and supporting code, that is not as harmful anymore. So something that would have been a very critical security issue, well, now you still need to fix it, but you have more time because an adversary needs always a second exploit to get out of the sandbox. And that the difficulty depends on the strength of your sandbox. Of course, this new file operation facade, the boundary layer between the host application and the sandbox code, can be vulnerable too. That is still written in a memory unsafe programming language, usually C and C++ and your core too. And if you have tainted data coming out of this file format parsing and decoding, you might still be able to lie about the length of data fields. And if your code taking this and using this data isn't careful about doing proper input validation, well, you still have the same challenges in the host application. But now by construction, by design, you prevented many security issues for a large amount of code, for hopefully a much smaller, maybe even a tiny boundary layer. And that's a great deal, I think. And there are two common approaches how to achieve this. And I suggest you review two browsers. The first one is, of course, Chromium, which has the basic idea, well, let's run everything in a different sub-process and have the sub-processes with as minimal privileges as possible to just get the job done. I'm not too familiar how that works on Windows, but privilege isolation can be achieved on Linux, for example, with seccomp, where you say only a specific set of system calls and maybe even only with specific parameters are allowed to be called. That way you can make it really hard to break out of a sandbox process. And the processes, of course, guarantee memory isolation. Another approach to achieve memory isolation is transpile to WebAssembly, WASM, and that is what Firefox does. There's also an open source project called RLBox. Seems not that well maintained, but there's a copy in the Firefox Git repository, so look at that. The idea here is take your library code, transpile it to WASM, and run it in the WASM interpreter. And you know, Firefox WASM interpreter is security hardened. That's what makes sure if you visit a random website, it doesn't get to control your computer or get access to another website's data. So reusing it for running codes that might have memory safety issues is a pretty awesome idea. And this WASM sandbox provides privilege and memory isolation. And I really like the idea of RLBox because it also allows you to integrate the sandbox in a highly iterative process. So let's look at why sandboxing. What are the pros and cons? The biggest benefit is probably it allows you to mitigate memory safety flaws of existing C and C++ code because it's kind of hard to ask people to rewrite it all. It's a proactive mechanism and it has strong, potentially very strong safety guarantees, and it enables you to focus just on the boundary or the interface layer between the sandbox code and the host application during security reviews. So you can spend more of your limited time on the parts of the code base that truly matter for security. Of course, cons too. There's a performance overhead. Platform compatibility issues, especially iOS, is a challenge because you're not allowed to spawn subprocesses or run interpreters. So it just doesn't work, but you can think about, does it truly matter for your threat model? An application on iOS is already sandboxed. strongly much better than a typical desktop app. Of course, for engineers, it's a challenge to work across the sandbox layer because it makes debugging harder, and it's sometimes hard to retrofit, more so for the process-based than the RLBerg's WebAssembly-based approach. And generally, if you have codes that is interaction heavy, that means calls to the operating system or user interaction, well, you have to figure out how to make these calls from the sandbox in a safe fashion. And of course, you have new risks at the boundary layer. So the fraction of code that is in the boundary layer compared to what you protect should be really, really small to make it worth it. And the third strategy is rewriting. And you can eliminate memory safety flaws by design. Well, use a memory safe programming language. And well, there are a bunch of them. The basic idea is, well, rewrite a library and make a memory safe library out of it. Ideally with a C-style library interface so that you can call it from your C or C++ based application, or pretty much any other programming language. So that's the lingua franca to expose stuff. And the coolest thing when I discussed this topic with some of my peers, they said, especially one person who mostly writes C++ code, it felt like they are finally writing software like it's the 21st century. They prefer writing libraries in Rust with a C-style interface to embed in or use in a C++ application. I found this very insightful. What kind of a difference this more modern approach makes. So what are memory safe languages? Rust and Swift are systems level programming languages, but Go, Java, Python, Ruby, C#, many others are considered memory safe too. Basically, when you as a software engineer can't accidentally introduce memory safety issues. So it reasonably eliminates most memory safety issues. And that doesn't mean it's absolute. In Rust, you can opt out of the safety by saying, well, this area is unsafe. Well, then you can still do whatever you want. But that is, for security people, much easier to review, because now you know these are the areas of the code base where I need to have a closer look and make sure it looks good. Back to the problem here, or to rewriting, there's still a boundary layer that is unsafe, similar to the sandboxing approach. But it's probably a little bit thinner, but the problems are basically the same. So why rewrite? Simply because it mitigates memory safety flaws by design. In a library that's completely written in a memory safe programming language, you can't have memory safety issues, and that's fantastic. If you focus on these file parsing or in general decoding and functionality, you can have a huge impact on the overall security of your system. With the next one, I'm a little bit more careful. I'm in security, so claiming developer productivity benefits is usually not something I do. But talk to your peers in engineering if they think adopting a more modern programming language than C or C++ leads to other benefits. And they can make a much stronger case than you as a security engineer. And with a rewrite, again, the same. It enables focus. Can focus on unsafe areas of the code. You focus on the boundary or interface layer again. The cons is, depending on the language, you have again compatibility issues. That is more so with Swift. And there was very recently an announcement that it might be getting better Windows support, but we'll have to see. For Rust, this is not really a problem. It runs on everything that I care for. The bidirectional interaction across language boundaries is still challenging, and that's why I said you need a C-style interface in front of Rust libraries. Combining C++ and Rust is still hard. Again, as with sandboxing, risks at the boundary layer, and engineers must learn new paradigms. Rust borrow checker. I still haven't done this work myself. I plan that for 2025 to learn a bit of Rust. It probably takes some time getting used to. But I believe long-term, the benefits of the ecosystem that also provides packages and additional correctness guarantees will outweigh these concerns. And if you happen to know how to solve the Rust C++ interaction problem, please reach out to me. I'd love to hear your thoughts. This talk is already kind of long, so I can't discuss all the strategies. You can use compiler flags to get defense in depth, address space layout randomization, stack canaries. There are lots of pros and cons, and you have to do your own research to figure out what makes sense in your specific context. What kind of mitigations can you afford? I'm also running the static code analysis program at Adobe, and I believe static analysis is not a good fit. So you can get some basic benefits by using a bit of static analysis to find flaws, but you'll probably have to deal with a lot of noise. So I have not yet found it useful. If you have a different experience, also let me know. I'd love to learn. That concludes the technical part of the talk, and unfortunately, I learned that this technical part is relatively easy to get right. You talk to your engineers; they'll figure out how to get this done. But driving change, that's really the hard part. So how do you get an organization, a large enterprise, to invest lots and lots of money into achieving memory safety? That's the real challenge I faced. This is a rough overview of the process I used. The first step is you have to ask yourself, is memory safety truly a top concern for the business? The business has limited engineering bandwidth. There are always other kinds of security issues. Are you focusing on the right things? Are you focusing on the right code parts within memory safety, as I discussed with the abstract desktop app to prioritize this? Do you maybe have data that can support your claims? Maybe you have a bug bounty program where people or other responsible disclosure where you are facing memory safety flaws. Are you facing 0 days? Collect all the data, and you need to be sure this is high enough priority to make it worth for both your security organization as well as the engineering and product team that you are, or product teams that you are going to ask. Because otherwise, if you go to their senior leadership, well, why invest in this if it's not a priority? They have to trade features, stuff that earns your income, your salary, to build this. So you need to have a very strong case. And I believe without having partners in the engineering organizations, you stand no chance. So I partner with staff plus or principal and senior principal engineers at Adobe to create a roadmap. How do we want to tackle memory safety and other concerns, and really form a partnership? They know best how to solve the engineering challenges, and you probably know best how to prioritize the security risks and pick really these parts of products and that matter most to your business and your customers. So security prioritizes the risks, engineering the technical approach, and be creative. The strategies that I mentioned are probably need to be creatively mixed to be a good fit for each individual product. Context, your threat model, that is what matters here. Then, of course, you need to frame the conversation in business terms. So you need to talk to business leader. And what I talked about is the looming threat of regulation. We are talking timeframes of 5 to 10 years, but memory safety, achieving that, well, it's not easy. That might take also 5 years to get started for real and make a dent in the problem space, especially if you have hundreds or maybe billions of lines of C++ code. You can do a little bit of competitive analysis. What are your competitors doing? What kind of programming languages do you use? Are they facing memory safety too? Are they investing in sandboxing, rewriting? You can also point at Linux or Microsoft. Both have embedded Rust in their kernels. Small parts still, but progress. Or Firefox, who has, of course, a lot of Rust code. You, not so much, but your engineering partners can talk about the benefits of adopting these memory safe languages because they provide correctness guarantees beyond memory safety. I'm hearing anecdotes that code written in Rust has a much lower rollback rate compared to C++ code. That can be impactful. And of course, you need to understand the risk to your customers and your business. This depends on if you have desktop apps, mobile apps, or stuff running in the cloud in a multi-tenant environment. So figure out these things. And then finally, you need to get it on the roadmap. That means building consensus with leadership, both in the security organization, that this is important, and in the product organization or organizations. And I generally use a dual strategy, bottom up and top down. What does it mean? And imagine I would be going to the vice president of one of Adobe's products and ask them, oh, let's work on this memory safety stuff and let's make a decision to invest. Not going to work. They'll ask their direct reports, oh, what do you think about it? We have never heard about it. And well, then you're already lost. So the bottom up means you need to figure out how to work with the people who support the big decision maker and get them to understand the challenges, the approach, and get them on board that this is a good idea. Once you've achieved this and the key people and your engineering partners know who these people are, that is why it's so important. Can get them all on board, and then you can have the conversation with the persons that have actually the power to put something that costs maybe 5, 10, 20% of your engineering bandwidth on the roadmap. That's the top-down approach. What this means in short is evangelize, 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 and evangelize even more. So sometimes I'm joking that I'm no longer a principal security architect. I'm a principal PowerPoint architect to get this stuff done. But it's really important to communicate well and use this dual strategy of bottom up and top down to drive change. And the last part is execute. Once you've decided on a strategy, execute it iteratively. It is of crucial importance to always keep the product shipping, independent of which strategy or combination of strategies you choose. Avoid creating forks of large code bases where the security is attached in a long-lived branch that takes 6 months, 9 months, 12 months, maybe even longer to build. Because there's always a race between the new and more secure version and the current version that needs more features all the time. So you want to avoid this race. Don't do big bang rewrites. Ship iteratively. There's lots of studies that, especially Dora by Google, that talk about that keeping shipping is really important to get quick feedback, and that creates more productivity. What I've presented today is a toolkit to create your strategy. So I purpose did not show Adobe strategy, how this all works, because I don't know your context. I don't know your threat model. I don't know your business situation. So I've presented to you a mental model to prioritize security risks. That is the abstract desktop app, the adversary model, and the n-click approach. I showed you strategies to mitigate the highest risks, like fuzzing, sandboxing, and rewriting. And I discussed one way to drive organizational change. So how can this look in practice? So there are different prioritization approaches that you can use in your threat model. You can look at code functions with a lower n-click distance. You can look at code with existing adversary interest, bug bounty, 0 days, and so on. You can also prioritize based on the feasibility to sandbox or rewrite. For example, you might say, well, sandbox by default, all the file loading libraries, because, well, you can put them in the same sandbox. That's relatively straightforward. And prioritize rewrites for things that cannot be sandboxed and fuzz everything else. Maybe you also have a need for visibility to understand where are the most memory safety risks. Well, then just do a lot of fuzzing at the beginning. So an example strategy could look like the following. Focus on file parsing and decoding libraries. Integrate a generic sandbox to mitigate exactly these risks during file parsing and decoding, because that gives you lots of coverage for a relatively small investment. Write new file parsing libraries exclusively in Rust with a C-style interface. And prioritize code for fuzzing where sandboxing and rewriting is not feasible, mostly the core of the application. Of course, you need to fine-tune this to your specific situation. All right. Thank you for watching my talk. There's also a PDF linked from this video with lots of references. Go take a look at it. Thank you.